Hello everyone, I am Muskan from Basic Chemistry Honors first year. My roll number is 21. Today I am going to read the chapter P block elements. The element belonging to group 13 to 18 constitute p block elements. These involve the addition of 1, 2, 3, 4, 5, and 6 electrons respectively in p orbitals, and s orbitals are already filled. The general electronic configuration for the atoms of this block is ns2 np126. Together with s block elements, these constitute the representative elements. These elements form very important compounds. In the present unit, we will have comparative study of elements of group 13 to 17 and their important compounds. The elements of group 13. The group 13 of the periodic table consists of elements boron, aluminium, gallium, indium, and thallium. Except boron, which is classified as a non-metal, all other elements of this group are metals. Aluminium is the most abundant of these elements. It is the third most abundant element by weight in the Earth's crust. Boron occurs rather sparsely. Gallium is twice as abundant as boron, but indium and thallium are much less common. Electronic configurations. The elements of group 13 have general electronic configuration ns2 np1, that is one electron in the outermost p orbital and two electrons in the s orbital. Their electronic configurations are given in the table. General characteristics of group 13 elements. The important physical constants of group 13 element are given in table and their general characteristics are discussed below. Atomic and ionic radii. The atomic and ionic radii of group 13 elements are smaller as compared to corresponding element of group 2. This is due to increase in nuclear charge. When we move from element of group 2 to group 13 in the same period, as we move from left to right in the period, the magnitude of nuclear charge increases, but the electrons are added to the same shell. Since the electrons in the same shell do not screen each other, therefore the electrons experience greater nuclear charge. In other words, effective nuclear charge increases and thus size decreases. Therefore, the elements of this group have smaller size than the corresponding elements of second group. On moving down the group, both atomic and ionic radii are expected to increase due to the addition of new shell. However, the observed atomic radius of aluminium is slightly more than that of gallium. While going from aluminium to gallium, there are also 10 elements of the first transition series of d block from atomic number is 21 equal 21 to 30, which have electrons in the inner d orbitals. The d orbitals do not screen the nucleus effectively because of their shapes and poor penetration power. As a result, the effective nuclear charge in gallium become more than in aluminium, and its atomic radius therefore decreases slightly. Melting and boiling points. The melting and boiling points decreases or moving down the group. However, the decrease in melting point is not regular as in boiling points. Ionization energies. The first ionization energy of group 13 elements are less than the corresponding members of the alkaline earth. This is because the first electron in case of group 13 element is to be removed from p orbital, while in the case of elements of group 2 the electron has to be removed from s orbital. Since p orbital are at slightly higher energy than the s orbital, the electrons in the atom of group 13 element is weakly held by the nucleus, and therefore the first ionization energy is less. However, second and third ionization energies are quite high. When one electron is removed from outermost p subshell, the resulting ion has completely filled s orbital. Therefore, it becomes difficult to remove the second electron. As can be seen from table 1, the ionization energy of boron is highest in the group. It decreases sharply from boron to aluminium, and then ionization energy of gallium is unexpectedly higher than that of aluminium. The decrease in ionization energy on moving down the group is due to the increase in atomic size and screening effect, which is more than to compensate the effect to increase in nuclear charge. Consequently, the electron become less and less tightly held by the nucleus as we move down the group. Hence, ionization energy decreases down the group. The sharp decrease in ionization energy from boron to aluminium is due to increase in size. In case of gallium, there are 10 d electrons in its inner electronic configuration. Since the d electrons shield the nuclear charge less effectively than the s and p electrons, the outer electron is held fairly strongly by the nucleus. As a result, the ionization energy increases slightly in spite of the increase in atomic size as we move from aluminium to gallium. The similar increase is also observed from indium to thallium, which is due to the presence of 14 f electrons in the inner electronic configuration of thallium, which has very poor shielding effect. Oxidation states. The atom of these elements have three valence electrons, two in s subshell and one in p subshell. Therefore, all these elements can show maximum plus 3 oxidation state. Boron shows consistently plus 3 oxidation state in its compound. Except boron, the other elements also show plus 1 oxidation state. The plus 1 oxidation state becomes more stable as we move down the group from boron to thallium. In case of last element thallium, plus 1 oxidation state has been found to be more stable than plus 3 oxidation state. Gallium, the third element of the group, appears to show plus 2 oxidation state in some of its compounds, such as GaCl2. However, it has been shown that this compound has the structure Ga positive GaCl4 negative, which contains gallium in plus 1 and plus 3 oxidation states. The cause of stability of lower oxidation state as we go down the group can be explained on the basis of inert pair effect. The elements of group 13 have 3 electrons in their valence shell, ns2 and p1, and therefore exhibit oxidation state of plus 3. However, it has been observed that in addition to plus 3 oxidation state, they also exhibit oxidation state of plus 1. The plus 1 oxidation state becomes more and more stable as we go down the group from boron, aluminium, gallium, indium to thallium. The plus 1 oxidation state of thallium is more stable than plus 3 oxidation state. For example, thallus compounds such as TLOH and TLClO4 are more stable than their thallic compounds. This is attributed to the inert pair effect. In the case of last element, after the removal of one electron from p orbital, the remaining ns2 electrons behave like stable noble gases and do not take part in compound formation. The reluctance of the s electron pair to take part in chemical combination is called inert pair effect. It helps to explain the stability of lower oxidation state for the heavier elements of the group. Electropositive or metallic characters. Due to high ionization energies, the elements of group 13 are less electropositive as compared to elements of group 2. On moving down the group, the electropositive character increases because ionization energy decreases. For example, boron is a non-metal while the other elements are typically metals. Tendency to form covalent compounds. The trivalent boron ion B3 positive is exceedingly small. Therefore, it would have greater polarizing effect on the neighboring anions. As a result, it would tend to pull off electrons from neighboring anions and thereby show covalent character. Thus, while boron generally shows covalent character and other elements exhibit ionic character also in its compound, for example, the compound of aluminium are both ionic and covalent. For example, anhydrous aluminium chloride is covalent while AlH2O6 3 positive is ionic. Comparative study of compounds of group 13 elements, hydrides. Boron forms a number of hydrides having the general formula BnHn plus 4 and BnHn plus 6. These compounds of boron and hydrogen are called boranes. For example, B2H6 diborane, B4H10 tetraborane, B5H9 pentaborane, B6H10 hexaborane, B5H11 pentaborane. The number expresses the number of hydrogen atoms present in the borane. These contain special type of bonds known as multi-center bonds. The simplest among the borane is diborane. Aluminium forms polymeric hydrides of the general formula AlH3 to the power n. It decomposes on heating above 200 degrees Celsius to its elements. Other members form less stable hydrides, indium hydride and thallium hydride are extremely unstable. These elements also form complex hydrides like lithium aluminium hydride, lithium boron hydride, lithium gallium hydride. The formation of these hydride is due to the presence of vacant p orbital in their outermost shells, which readily takes electron pair from hydride ion. In these hydrides, the hydride ion acts as an electron donor. The alkali metal tetrahydridiborates are predominantly ionic in character, while LiBH4 has some covalent characters also. It reacts violently with water, liberating hydrogen. NaBH4 reacts slowly with water and may be recrystallized from cold water with only slight decomposition. KBH4 is quite stable in water. The stability of these complex hydrides increases with increasing size of the cation. These are particularly lithium aluminium hydride and sodium aluminium hydride act as powerful reducing agents. They are used to reduce aldehydes and ketones to alcohols and nitriles to amines. The borohydrides of beryllium and aluminium have considerable covalent character. In these, the BH4 negative group has tetrahedral geometry. These borohydrides are discussed in detail later on the chapter. Lithium aluminium hydride is also prepared by the action of lithium hydride with aluminium chloride in ether. As it is very powerful reducing agent, the complex hydride can also be prepared by similar method. Aluminium borohydride is prepared by reacting sodium borohydride with anhydrous aluminium chloride. Oxides and hydroxides. All the elements of group 13 form oxides of general formula M2O3, in which the oxidation state of the element is plus 3. For example, B2O3, Al2O3, Ga2O3, In2O3, Tl2O3. They also form hydroxides of the formula MOH3. The principal oxide of boron is B2O3 and is commonly known as boric oxide. It is anhydride of orthoboric acid H3BO3 and is obtained on dehydration of this acid by heating at 100 degrees Celsius. It is highly stable substance but hydrolysis in water giving boric acid H3BO3. The oxide of aluminium Al2O3 is commonly called alumina. It is obtained by heating aluminium in oxygen. It also occurs in nature in various forms such as alpha Al2O3 corundum, gamma Al2O3 activated alumina. Gallium oxide Ga2O3 is also formed by direct combustion of gallium and oxygen at moderate heat. It is a white crystalline solid. Indium oxide is formed by heating nitrate sulfate of the metal. It is yellow solid. Thallium forms two oxides Tl2O and Tl2O3, in which oxidation states of thallium is +1 and +3 respectively. Tl2O is more stable than Tl2O3. The hydroxides are generally obtained by dissolving the oxides of the element in water. However, boron oxide does not react with water even in the form of steam. The oxides and hydroxides of boron are weakly acidic and therefore react with alkalis. Aluminium oxide and hydroxide are amphoteric in nature. They dissolve both in acid as well as in alkalis. Like AlOH3, GaOH3 is also amphoteric. Indium hydroxide and thallus hydroxides are basic. Therefore, the basic character of oxides and hydroxide increases as this. This can be explained on the basis of the ionization energy of the element. As we move down the group, the magnitude of the ionization energy decreases. As a result, the strength of the metal oxygen bond also decreases accordingly. Therefore, its cleavage becomes easy, resulting in the increased basic strength down the group. The acidic strength of hydroxides therefore decreases. Oxoacids, boric acid. Among the oxyacids of group 13 elements, orthoboric acid is important. It is normal end product of hydrolysis of most boron compounds. Several boric acids are known. All of them are derived from boron trioxide having varying amount of water. For example, orthoboric acid, metaboric acid, pyroboric acid, tetraboric acid. Out of this, orthoboric acid is most important and is commonly known as boric acid. Structure of boric acid. Boric acid has the unit BO33 negative ions and BO33 negative ion. The boron atom involve sp2 hybridization as described below. Boron atom in the ground state has the outer electronic configuration 2s to 2p2. In the excited state, one of the electron from 2s orbital is promoted to 2p orbital, making 3 unpaired electron. The boron atom undergoes sp2 hybridization and each sp2 hybrid orbit of boron overlaps with 2p orbital of oxygen ion, forming 3 BO bonds. The BO3 negative has trigonal planar structure as shown in figure. In orthoboric acid H3BO3, BO33 negative units are bonded together through hydrogen bonds into two-dimensional sheet. The hydrogen bonding in one H3BO3 unit is shown in figure and complete structure is shown in figure. It is evident that each boron atom remains bonded to three oxygen atoms and each oxygen atom is bonded to a hydrogen atom. Halides. All the elements of group 13 form halides. Most of these elements form trihalide of the formula MX3 by pairing of 3 electrons of central metal atom with 3 electrons of 3 atom of halogen. They are also they also form lower monohalides MX2 which are unstable. Trihalides. Boron forms covalent trihalides BF3, BCl3, BBr3 and Bi3. Aluminium also forms the trihalides with all the four halogens AlF3, AlCl3, AlBr3 and Al. I3. Among these, AlF3 is ionic while the remaining halides are covalent. Among the trihalides of other elements of the group, the trifluoride of gallium, indium, and thallium are involatile and have much higher melting point and heats of formation than other trihalides. GaF3 melts above 1000 degrees Celsius. INF3 can be prepared by thermal decomposition. TLF3 can be prepared by the direct fluorination of Tl2O3 with fluorine BrF3SF4 at 300 degrees Celsius. It is stable up to 500 degrees Celsius. GaCl3 is a white solid melting at 780 degrees Celsius. Its vapor at 500 degrees Celsius consists mainly of dimers having the formula Ga2Cl6 in Cl3, however, does not dimers. It is relatively more ionic than CaCl3. Indium I3 is, however, dimeric. TlCl3 does not dimerize and is more ionic than even InCl3. It decomposes to TlCl and chlorine above 40 degrees Celsius. TlBr3 slowly gets converted to this at room temperature. TlI3 is ionic compound containing thallium and linear triiodide ion. Lower halides of elements of group 13. Boron forms dihalide of the type B2X4. For example, B2Cl4 is formed by passing electric discharge through BCl3 vapor between mercury or copper electrodes. In the solid state, it has planar structure. B2F4, B2Br4, and B2I4 have also been prepared, but these halides are less reactive than the corresponding trihalides. Gallium and indium also form dihalides. Monohalide of boron. Boron forms polymeric monohalides. The compound B4Cl4, B8Cl4, B9Cl9 are crystalline solids. These possess closed cages of boron. The structure of B4Cl4 is shown below. Aluminium, gallium, indium, and thallium form monohalide in the gas phase at elevated temperature. These are covalent compounds, and many of these are quite unstable. For example, AlF, GaF, INF are unstable gases. AlF3 is most unstable and decomposes readily. Other monofluorides also decomposes but less readily. In a similar manner, in general, the monohalides of other halogen are more stable than monofluoride. Other example gallium, indium chloride, bromide or iodide are more stable than gallium fluoride and indium fluoride respectively. Thallium halide are the most stable amongst the monohalide of group 13 elements. Monohalide in general can be prepared by heating the trihalides with the metal. Indium halide can be prepared by heating indium in a current of halogen or by heating it with mercuric halide. Thallium halides can be easily prepared by reacting thallium salt with the appropriate alkali halide or an acid. Anomalous behavior of boron and resemblance with silicon. Boron is the first member of the group and has different characteristics from aluminium and other members of the family. This is because of its small size, high ionization energy, and electronegativity. Absence of d orbital in its valence shell. Anomalous behavior of boron. The following properties show anomalous behavior of boron in comparison to aluminium. Boron is non-metal while aluminium and other metals of the family are metals. Boron is a bad conductor of electricity whereas aluminium and other members are good conductors. The melting and boiling point of boron are much higher than those of aluminium and rest of the family members. Boron exists in two allotropic forms, that is amorphous and crystalline. The other member of the family do not show any allotropy. Boron forms covalent compound whereas aluminium forms covalent as well as ionic compounds. The other member of the family form mainly ionic compounds. Boron forms a series of hydrides called boranes which are quite stable. The hydrides of aluminium and the rest of the member are polymeric and are less stable. The oxide and hydroxide of boron are acidic, whereas those of aluminium and gallium are amphoteric. Indium and thallium form basic oxides and hydroxides. The trihalides of boron exist as monomer, while those of aluminium exist as dimers. Boron shows maximum covalency of 4 in its compound. Iron, Aluminium and other members can show a covalency of even 6. Boron combines with active metals such as magnesium to form magnesium boride. The other elements do not combine with magnesium. Diagonal similarities of boron and with silicon. Boron shows diagonal similarities with silicon. Some of the points of similarity between boron and silicon are given below. Non-metallic character. Both boron and silicon are non-metal and have high melting points, high ionization energies, and are poor conductor of electricity. Allotropy. Both exhibit allotropy and exist in amorphous and crystalline forms. Formation of hydrides. Both boron and silicon form a large number of hydride. These hydrides are volatile and readily catch fire when exposed to air. These are also easily hydrolyzed. Formation of oxides. Both the elements form stable solid oxides which are weakly acidic in nature. In water, they give the corresponding weak acids, namely boric acid and salicylic acid, to form metaborates and metasilicates. Hydrolysis of halides. The chlorides of both boron and silicon are readily hydrolyzed by water to boric acid and salicylic acid. Due to liberation of HCl, they fume in air. Similarly, boron trifluoride and silicon tetrafluoride get hydrolyzed hydroxides. The hydroxides of both boron and silicon are weak acid. They do not show several any basic character. Formation of borides and silicides. Boron forms a number of binary compounds with several metals known as borides, and silicon forms metal silicides. Some of the borides and silicides undergo hydrolysis to give boron and silicon respectively. For example, boron and silicon react with magnesium. Both magnesium boride and silicide react with acids to give mixture of boranes and silane respectively. Semiconductors. Both boron and silicon in elemental form are semiconductors. Formation of ester. Acids of both boron and silicon form volatile ester when heated with concentrated H2SO4. Chemistry of some important compounds. Diborane. Diborane is the simplest of the boranes and is one of the most important members. It formed the starting material for the preparation of other boranes and it is also one of the synthetically useful reagent in chemistry. Preparation of diborane. Diborane can be prepared by following method. First, diborane can be conveniently prepared in small quantities, laboratory quantities, by reaction of iodine and sodium borohydride in decline. It can also be prepared in small quantities by the reaction of sodium borohydride with anhydrous phosphoric acid. Third, it is quantitatively obtained by the reaction of sodium boron hydride with boron trifluoride in ether at room temperature. Diborane can also be prepared by the reduction of boron halides and reducing agents like lithium hydride, sodium hydride, calcium hydride, lithium aluminum hydride. It can be prepared by passing silent electric discharge through a mixture of hydrogen and boron trichloride at low pressure. On an industrial scale, diborane is prepared by reducing gaseous BF3 with sodium hydride at 180 degrees Celsius. Properties of diborane. The important property of diborane are physical state, it is colorless gas, boiling point 92.6 degrees Celsius, melting point 164.9 degrees Celsius with a foul smell. Stability. Diborane is stable only at lower temperatures. When heated at temperatures between 100 degrees Celsius and 250 degrees Celsius, it changes to a number of higher boranes. The careful control of temperature, pressure, and reaction time enables the yield of different boranes. For example, B4H10 is the best prepared by storing B2H6 under pressure at 25 degrees Celsius for 10 days. Thank you.